Okay, welcome everyone. Welcome to this webinar on light as a cosmic messenger. My name is Julie. I'm the director of Discover the Universe, and I'll be presenting this webinar today. Before we get started, I just want to welcome everyone who's online with me right now. There's quite a good crowd right now from different countries. That's awesome. And welcome to everyone watching the recording. So if you're new to Discover the Universe, please know that everything is recorded. So if you can't be there live, it's always nice to be there live because you can ask questions. But if you can't, no worries, you can watch the recording. And if this is what you're doing right now, and if you have any questions as the webinar goes on, please email me. I'll be happy to answer your questions. Any emails you receive from Discover the Universe goes to me. So just reply to one of those and I will receive it. So I'll just take a minute to introduce Discover the Universe if you're not familiar with it, although I recognize many names and I know many of you probably could give this little speech by yourselves because I think many people come back very often. So we try to train educators, teachers and informal educators to help them teach astronomy. So whether you're teachers in class or in a museum, a science center, a volunteer going to classrooms, and if you'd like some help with astronomy, we're here. Almost everything we do is online and free, so you can register, through webinars like this one here. So we're available everywhere in Canada, but actually worldwide. And I see we have some people from the other side of the Atlantic right now, which is great. We do everything in English and French. So this webinar was offered yesterday in French. If you know some people who teach French immersion would like to have access to it, they can still access it. And our future programs are in French as well. We want to thank our financial supporters, mostly the Dunlap Institute at Toronto, which became our main partner a few years ago. We're also supported by astrophysicists across the country, so the Canadian Astronomical Society, and also the CAC. The logo didn't show up here for some reason. The Center for Research in Astrophysics in Quebec. So basically, scientists, astrophysicists across Canada are supporting this initiative. I want to tell you about our upcoming workshops. Our next webinar will be in May, on May 17th. It will be about exoplanets, so those planets that we're discovering outside the solar system. Very interesting topic. It will be called Looking for Other Worlds. And we have a great speaker, Jason Rowe. He presented in our first few years, I believe it was maybe 2013 or 14, when we started offering webinars. He's an expert on exoplanets. He worked for the Kepler telescope. He's now a professor at Bishop's University here near Sherbrooke in Quebec. Great communicator, so I'm glad to have him back for this webinar. And what we'll be doing for this one, so usually our webinars are mostly for teachers, and then you can take the content and present some parts back or whatever, use it in the classrooms. This one is open to teachers with their students. So it will be aimed to the students directly. It's at 1 p.m. Eastern. Of course, if you can't be there live again, the recording will be available, but we decided to open this one for students as well. It's offered during a Science Odyssey in Canada, so the National Celebration of Science and Technology. So anyway, go check on our website. The information is there, but I look forward to hearing Jason again talk about the latest research on exoplanets. And we also have a few on-site workshops. So if you'd like to meet me in person, and if you're in the Toronto area or Victoria, I will be in Toronto on April 28th. Again, the pages are available for registration on the Discover the Universe website. And we are following the CASCA conference, so the Canadian Astronomical Society. Their annual conference this year is in Victoria. And we're offering a workshop for elementary and middle school teachers on May 23rd, and then secondary school teachers on 24th. Next year, we'll be in another city. Last year, we were in Edmonton. So anyway, this is kind of fun to travel around the country and offer on-site workshops. There we go. Okay, so if you'd like to follow us on social media, we also have those available. The links are on our website, which is right there. I'm guessing you all know about our website, but in case someone sends you the link to the recording, I just want to make sure you know where to find us. Okay, now let's talk about light as a cosmic messenger. The original idea for this workshop, for this webinar, which I originally presented 3 years ago. So if you've been following us for a while, maybe you've seen this one. Of course, it's updated with new info as well. But I decided to repeat it because it's it's something. It's the basis. It's everything about astronomy is about light. Almost everything. I'll come back to that more at the end. But what we know about the universe, we study mostly through light. So that was the idea of it when I came up with the idea of this webinar, was to tell people, how do we know? How can we study objects so far away and know quite a bit about them? There's no way we can travel there. We don't have a sample we can bring back to Earth and put in the lab. So how do we know all this information? And it's because we can study light. And there is so much information that we can decode from the light of these objects. So this is what I'm going to tell you. I'm going to tell you a bit how we do all this. So let's start with a basic question. What is light? Well, light can be is an electromagnetic wave. Now, this is a bit tricky to imagine. Right now, there's a lamp in front of me, and there's also the window, so there's light coming in. And I would have to imagine that there's an electric field and a magnetic field oscillating at 90 degrees from one another. And this is the light that's coming to my eyes, and I can see my computer or everything around me. It's pretty hard to visualize, so we kind of sort of need to accept that and take it from there. If you try to imagine all those little waves around, it's a bit tricky, but it is a wave. And why I'm telling you that, because we'll come back to the term wavelength quite often in this webinar. So wavelength is just, for example, the distance between two peaks of those waves. If you think of a wave, in the water, for example, or any 2 points you would take and measure the distance, that would be what we call the wavelength. So we'll come back to that in a bit, because light can have different wavelengths, and some of them are more stretched. Some waves are more stretched than others, and that we see those different wavelengths as colors, for example. But light can also be thought of as a particle, or many, many particles hitting your eyes, for example. And this is tricky. The light-particle duality of light is, the wave-particle duality, it's, again, something very tricky to think about. It's kind of weird that it can be both a wave and a particle, but again, this is something, I won't go in all the quantum details of all that, but we just have to accept here. Mostly what I wanted to tell you about this is when we talk about photons. So a photon is a particle of light. So in astronomy, for example, and we use both representations of light all the time. Scientists will talk about photons hitting the camera, for example, and that will be, the number of times that light hit the camera. Photon count. Sometimes we even count the photons that hit the camera. So obviously, it makes sense to think of light as a particle as well. So it kind of has both properties, and that's all I'll say about it for now. But if you hear a photon, it's a particle of light. And depending on its energy, then the wavelength of the light, we can sort of translate that into the energy of the photon. So we can see photons with different energies as different colors, in a sense. In a vacuum, light travels at about 300,000 kilometers per second. That's the speed of light. And according to Einstein's theory of relativity, nothing can travel faster than this. So this is the ultimate speed in the universe. But the speed of light is very useful in astronomy because we use it to calculate distances. So 1 light year is the distance that's traveled by light in 1 year. So even though it has the word year in it, it's actually a unit of distance. So if you imagine that light travels at 300,000 kilometers in 1 second, now imagine how far it can go in 1 year, and that's 1 light year. It's a very, very big distance, 10,000 billion kilometers. So even though I can tell you how to calculate it, this definition, the number, my brain still doesn't understand exactly how big it is, because it's just completely beyond our other references that we're used to. But I wanted to mention that because a telescope is basically a time travel machine when you think about it. Light travels fast, but it's not infinitely fast. When you turn on the light in your room, for example, suddenly there's light everywhere. It's actually traveling from the light to the walls, for example, and bouncing back in your eyes. But it's doing that so quickly that you don't notice it. If you're looking at objects that are very far away, however, it does take some time for the light to reach your eyes. So if we look at a star that's 100 light years away, we see it the way it was 100 years ago. So we're looking in the past. And if you look at, for example, an image like this one is one of the Hubble, this one is the extreme deep field, if I remember right, one of the some of the images taken by the Hubble Space Telescope that show some of the furthest galaxies ever photographed. So some galaxies in this image are billions of light years away. Actually, some of them are over 10 billion light years away, which means we see them the way they were 10 billion years ago. It took that long a time for the light to reach us. So they're probably very different today, but what that means for us is that as we look further out in space, we're looking further back in time, and that allows us to see how galaxies evolved. If we look at a galaxy 10 billion years ago, there's a good chance that it doesn't look the same as galaxies that are nearby because we're looking at the way it was a long time ago in the universe. And in fact, this is a bit the goal of many telescopes, and the James Webb Space Telescope, which will be launched. It was supposed to be next year, and I think it got delayed by another year. So I think now it's 2020. But anyway, it's going to be the next space telescope, and it will be looking in infrared mostly. I'll come back to that. But its goal is to look at sort of first stars and first galaxies that were formed in the universe. So really looking very far out in space, so that we're looking back in time and not long after the Big Bang. So this is something interesting about telescopes. You can think of it as a time travel machine. We're looking back in time as we look further out in space. Now, let's talk about visible light. And this is kind of weird when you think about it. If there's visible light, that also means that there is invisible light. And there is invisible light. It doesn't make sense to think at first, but there is light that we can't see. Our eyes are not sensitive to other types of light. So our eyes can perceive different wavelengths of light as different colors. And we can see light with wavelengths between 400 nanometers and 700 nanometers roughly. So here you can see, you've seen this rainbow before, when you take the white light, actually I'll come back to that. When we take white light and we break it down into the spectrum or a rainbow, so a spectrum is exactly the same thing as a rainbow, it's just the scientific term for it. Here we have white light and it's going, through a prism. Here we get the rainbow. Or even if you don't have a prism, I'm sure you've all seen that when you take a CD or a DVD, and because of all the lines on the CD or the DVD, then it creates, it breaks down the light into all the different wavelengths or colors, and we can see that as well. We can create a spectrum this way. So if we come back here, so the light that we can see with our eyes goes from roughly 400 nanometers. So we have 380 here. So 400 is somewhere in violet, all the way up to 700 in the red. But it goes on here. You can see here 750, and beyond that would be infrared, for example. Infrared is a light. It's invisible light that we cannot see with our eyes. So as soon as scientists realize that there is some types of light we can't see, if we are able to have detectors to detect those types of lights, then we're learning about things we didn't know otherwise. Some things will emit in the infrared that we couldn't see in the visible, for example. So it opened up a whole different field in astronomy when we started using infrared telescopes and radio telescopes, and I'll come back to all that in a minute. We're used to that a bit with sounds as well. We know there are ultrasounds, sounds, for example, that animals can hear, some animals can hear, but we can't hear. So our ears can hear some sounds, but not all frequencies. And if the frequencies are too high, ultrasounds, then we don't hear that. Same kind of idea with our eyes. Our eyes are light detectors, and they only see within a certain range. And if you go beyond that range, there is some types of light there, we just don't see it. And what's interesting, again, the different the different wavelengths for us, it means different colors. So you can see, anything between roughly 450 and 495 is what we would call blue, and then green and yellow. And I find that kind of strange that sometimes we're teaching kids about the 6 or the 7 colors of the rainbow, and we're trying to have them learn them in order and so on, when it's really a continuum. There's no set limit. So if someone sees different colors a bit differently, maybe they might see 8 different colors in there, and that would be completely fine. It's a continuum. It depends where we want to decide, what we want to decide if we cut a color here and here is the next one. Oh, and I've been talking about nanometers, and I've been forgetting to explain what it is. You see it there anyway. Nanometer is 10 to the minus 9 meters, so it's extremely small. It's 1 millionth of a millimeter. And that's so our eyes can see 400 to 700 nanometers in terms of wavelengths. So if you're trying to visualize the waves, they're very, very small waves. The peaks are very close to one another, and that's visible light. But the visible part of the spectrum is only a tiny part of the entire electromagnetic spectrum. So remember I told you that light is electromagnetic waves. So if you look at all the wavelengths at which those waves can, all the wavelengths those waves can have, then the visible part is just a tiny, tiny part of the whole spectrum. So visible light is here. We talked about infrared. So if we go beyond red here, we have infrared, then we have microwaves, then we have radio waves. So and you can see the waves here, so certain wavelengths is here, longer wavelengths, then you get into the radio waves. These have longer wavelengths, lower frequency, and lower energy. If we go to the other side, then beyond violet, you've probably heard of ultraviolet waves before. So it's a type of light, it's just a type of light that we can't see. And beyond ultraviolet, then you have X-rays and gamma rays. And this way we're going with shorter wavelengths. You see the peaks are very close to one another. Higher frequency and higher energy. Higher energy also means that these types of waves are more dangerous to us compared to the very low energy radio waves, for example. And again, this is a continuum. The way we've split them into, well, visible part is really because that's what we see. But infrared, the difference between infrared and microwave and radio, some part of it is historical, how we discovered them, for example, X-rays. And some of it is just the kind of detectors that we use to detect those waves, the kind of technology we use to work with them, because it's really a continuum. So between, an infrared wave here and a microwave there, there's not much difference, just that it's a tiny bit more stretched. But the way we detect those overall are different from one end to the other, obviously. So one way to think about all that, and if it's new for you, it's kind of hard to wrap your head around that sometimes, that all these are just different types of light. But basically, because they're different wavelengths, they're sort of colors that we can't see. Sometimes I talk about those this way, especially if people are not familiar with wavelengths. Then I'll just say those, X-rays are basically just a kind of color that we can't see, a very energetic color that we can't see. And infrared and microwaves and radio waves, same thing. So because we see different wavelengths as colors, that kind of makes sense to us. We know what colors are. It's harder to imagine a color that we can't see, but in a sense, that's what those are. And I like to mention that when we talk about radiation sometimes, infrared radiation or radio waves or gamma rays and so on, we tend to think of it as, sometimes it's kind of a scary word, but it's not necessarily dangerous. A radiation simply means it's an emission or a transmission of energy, and not all of it is dangerous. Some types of rays here are more dangerous than others, like X-rays and gamma rays, the more energetic ones, but not all of them are dangerous to us. I mean, we're under visible light all the time, and we're okay. Okay, so now that we know that all those terms are simply different types of light, how can we use them to learn about objects? Well, we can use them on Earth and we can use them in space as well. But let's start with a few examples on Earth. You've probably seen thermal imaging before. So if we use infrared cameras, basically infrared is a measure of heat in terms of the kind of temperatures that we have here on Earth anyway. So if we look at, for example, here we all see the giraffe, no problem. But the giraffe glows in the infrared. So if we take an infrared image of the same area, then the giraffe will be brighter. Now, I want to explain something about this image here because we can't see infrared. So how come we can see this image? Well, what the sensor is doing is basically telling you where you're getting more infrared and where you're getting less infrared. So this area here is where the detector is detecting a lot more infrared radiation coming in. That means, so we can put it in colors. In this case, we put it sort of brighter and yellower, but it could be a black and white image with this one being brighter in terms of more white. We're getting more light from this place and less infrared light from the other places. So we're translating something that we can't see into something that we can see using computers and using colors sometimes as a color coding for the pictures. So in this case, everything that's yellow represents more infrared radiation from this object, and in this case, we can see that the giraffe glows. In fact, we tend to think that we can't. Actually, we would glow in infrared as well. Animals, humans, the same. We emit some heat, and that means we glow in infrared. And sometimes when we talk about planets and stars, the main difference that we say is that planets don't shine on their own. They reflect light from the sun. That's true in visible light, but they do shine in infrared, and especially Jupiter, for example, which has its own source of heat, internal source of heat. Jupiter glows in infrared. So it's a bit tricky when you say it doesn't shine on its own, it reflects light. It's true for visible light, but it does shine in infrared because of the heat. So anyway, this is an example of the giraffe that you've probably seen before. These are the kind of images, non-visible light images that people are most familiar with. We can also see different things in infrared, and this is an interesting picture here because infrared can go through the plastic bag, so you can see the person's hands quite well under the bag, but it doesn't go through glass. So you can see how the glasses are very dark here. We don't see the heat from the person's eyes because the glass blocks the light completely. So what I want to show you with these is that using infrared or the other kinds of cameras, other types of cameras using other types of light, we can see details we wouldn't be able to see otherwise if we just use the visible light image. And one experiment you can do, most remote controls work with infrared light. So here, though, if you look, but usually most of the time what happens is that if you press a button where the little infrared signal is sent off the remote control, you don't see anything. However, digital cameras can be sensitive to infrared light a little bit, and you can see the light if you look through your digital camera. It's not super bright. It depends on the kinds. It depends on the camera, but most cameras found on cell phones or just as I'm showing it to you, I have messages appearing on cameras or iPads or iPods and so on. All those tablets, things, electronic devices. Most cameras they will be sensitive to visible light, so we can see what our eyes can see. But sort of their eyes are a bit more sensitive in the infrared than our eyes, so they can see a bit beyond and enough to see the signal from remote controls. So this is an experiment you could do yourself. Or you can try it in class or ask the students to try it at home. For once, you could ask your students to take out their cell phones, iPods, or whatever other electronic devices they have that has a camera. But I've done it before in front of the whole class, and some people were able to see it. Lately, I found that they need to be quite close to the remote control to see it. So you need to look at the remote control through the camera on your cell phone, for example, and you will see the little light appearing. So again, it's kind of a translating an infrared signal into just light, so brightness, basically. So you see this, it gets bright when we press the buttons. I don't know if some of you are live with me right now. Have some of you tried this experiment? Have you been able to see the light from the camera? Kind of curious. But I'm sure you'll all be trying it. Maybe some of you are all gone in your place trying to find a remote control and try it with your cell phone right now. It's kind of fun to try. And it's worth showing to students. I find that things you can't see with your eyes, that there's stuff that we can't see. There's the world beyond what our eyes can see. See, Gavin has tried it. Awesome. Now, if we turn our eyes to, sorry, Mike, I see you have a question. Is all red light the same? I'm not sure exactly what you mean, but from what I understand, your question, no. In the sense that you would have some red lights that are specific one wavelength, like a laser, for example. Some red lights are more a broad spectrum, so they have different wavelengths in there. And I don't know I don't know if that was related to infrared light. Maybe the wavelengths of the infrared remote control. If that was the question, most remote controls Oh, okay. So it had nothing to do with remote controls. Red paint. No, they're very different. Actually, if you look at something red, and I'm trying to see if there's anything around me that's really red, um, it's it will not be just one wavelength. Most of the time, even if you have a blue shirt, there might be a bit of red in it. So it's a mix of wavelengths. It's not one pure wavelength. Something that's usually a pure wavelength almost is a laser, for example. But most other colors and red, like paints or lights, there are multiple wavelengths, and you will get a mix, mostly red, but you will get some yellow and some blue in there as well. Definitely in the paint, that would be the case, for example. So the colors that you have around you are not pure. I guess that's how we could say it. They're a mix of different colors. A very pure color, again, would be a laser, which has one specific wavelength. Okay, so you've seen this image already for a minute or two. Now, what if we turn our cameras to the sky? Let's say an infrared camera to the sky. What do we see? And here's an example of how different things can look. Invisible light, you might recognize the constellation Orion right here with the big star, the red supergiant Betelgeuse, Orion's belt, Orion's sword with the Orion Nebula, and the 2 feet with Rigel. Now, if we look at the same area of the sky but with an infrared camera, this is what we see. And as you can see, there's a lot more than meets the eyes, in the sense that you see a lot of gases, a lot of regions that have a lot of gases. You can see the Orion Nebula, this whole region here that has glowing gas in infrared. So it's not super hot gas, but it's in a sense that it's hotter than than the universe itself, or the interstellar space, and it's hot enough to glow in infrared. So we can see that here. This is where many stars are formed, and you can see it there. You can see different regions, for example. So it really gives you a different perspective on the sky. And there's different processes happening there. Thermal imaging is one thing in infrared, but there's also ways to look at some molecules will emit in infrared, so that could be a way, for example, to detect the molecules if they're glowing, for example. I see a question from Ed. Would that gas be the result of supernova explosions? Probably some, but mostly in some cases here, these are mostly star-forming regions. The Orion Nebula, is a huge region where stars are formed, and we can see that it glows quite bright here. Here we also have the Horsehead Nebula and different gases, but the whole Orion area has a lot of gas in it, and we can see it in this image. But definitely we say it's a star-forming regions, but stars that wouldn't live for very long might have exploded already as supernovae, so there might be some in there. Now let's look at another wavelength. So let's look at ultraviolet. You see two pictures here. This one is taken with a normal camera, the way we're used to. This one here is taken with an ultraviolet camera. And again, translating it into something we can see. Now, I'll give you a minute. What do you think this person has on the face, of half the face, for it to be so different? Like, we don't see any difference here, and here there's a huge difference between the two sides. Any idea of what that could be? Oh, Gavin got it already. Yes, sunscreen. So when you put sunscreen on your face or anywhere, basically, this person puts sunscreen on half his face. And sunscreen, what it does, and I actually thought at first that it was reflecting ultraviolet, but no, it's absorbing. So the sunscreen itself, the lotion, absorbs ultraviolet, so it doesn't get into your skin. It's absorbed in the lotion itself. And what that means here is that this side appears darker. The ultraviolet, it's like this part does not emit any ultraviolet at all or reflect any ultraviolet. It's just absorbing it, so it appears darker. It's kind of fun to see the difference. That again, something we can see with our eyes and something that's invisible light, we can definitely see here. So in this case, how we would see this person in ultraviolet is that the person, our face and everything is reflecting ultraviolet, except for this part, which is absorbing it, and then it appears dark. So it's kind of fun to show students examples on Earth of those different wavelengths and see that it's not just something that relates to space. Those differences can be seen all around us as well. But it's kind of fun to look at celestial objects in different wavelengths as well. So a few years ago, 2 years ago, we created a module about the sun. It's called the solar cycle, and I'll give you the link to it at the end. It's on our website. It's all free. You can check it. But we're using a tool called HelioViewer. You have the address right there. And when you start HelioViewer, you can change the dates. Anyway, I won't go in all the details, but basically it gives you the images from the latest, some of the latest images from observatories in space watching the sun. And you can see the images in visible light. So this would be an example of a visible light image of the sun. For example, many of you probably had eclipse glasses last summer to look up. This is the kind of image you would get. This is the kind of image that you have right there. So it's in visible light, but with a filter, so we can see the surface. And in this case, I knew in September we had some amazing sunspots, so I just put September 5th, and you can see big sunspots right there. Now you can change the instrument here and the measurement to see the sun in ultraviolet. So same day, but the sun in ultraviolet. So again, they translated that anything that's brighter yellow means more ultraviolet, and when it's darker, there's less ultraviolet hitting the camera. And they've color coded that one into a sort of yellowish tone. Different wavelength. There's sometimes they color code their different ultraviolet images in two different colors. So you can have many different ultraviolet images that use different wavelengths in ultraviolet. It's not just one ultraviolet, it's many of them. A bit like you could have an image in red and blue and green. They can have many ultraviolet, and they color code them differently. So this one is in yellow. But it's interesting to compare the two images, and you can even superimpose, like put them one on top of one another in HelioViewer. So this is what I've done here. I have two layers. You can see how the sunspots are mostly where you have some of the activity in ultraviolet, but not everywhere. So it's kind of fun to play with that and see how things look different in one wavelength and the other. So I invite you to check out HelioViewer, and again, I'll give you the link at the end. It's one of the modules that we have in our resources section on our website. We invite you to try it, and we give you more details than what I just gave you. This is just a 2-minute introduction to it. Now let's look at other celestial objects. The Crab Nebula, which is a supernova remnant. So we're talking about supernova just a minute ago. This is a star that exploded almost 1,000 years ago. It's a huge cloud of gas that's expanding into space, and this is what we see. This is a Hubble telescope image. So roughly the visible light version. It's not completely real colors. I'll come back to that at the end. But it's an image of what we could see with our eyes. If we do look at it with different wavelengths, we see things very differently. Radio image of M1, the first object in the Messier catalog, that's the Crab Nebula. Radio image, infrared, visible light, we see all those filaments. Ultraviolet, X-rays, looks completely different, and gamma rays as well. And in fact, it's by using X-rays that we've noticed that there's something very interesting happening in the center. There's actually a pulsar in the center. No, actually the pulsar was discovered, using radio waves. The pulsar is sort of a dead star, a very dense, it's a neutron star, so it's a very dense star orbiting very quickly, spinning very quickly on its own axis, and it has jets of radiation, and when those jets come facing you, it kind of looks like you're getting a pulse. So you get pulses like that. So this was, you can see that in radio. We can definitely see that there's some radio waves being emitted by this object. And in X-rays, you can see the sort of matter spinning around the pulsar. There's some jets here, gamma rays. When things are glowing in X-rays and gamma rays, you know they're very energetic phenomenon happening there. Because you need to do something that's either very fast or very hot or a lot of energy to emit in X-rays and gamma rays. So that's why this object is interesting, because it glows in many different wavelengths. Again, these were color-coded into the different wavelengths. So the blue here has nothing to do with X-rays. We could have put it red or yellow or whatever. It's just sort of white shows you where there's more X-rays coming from this part, and each pixel basically tells you in that part of the object how much X-rays it's getting. Is it a lot or less? Add another question, maybe a silly question, but do we know of any animals or birds that can see in UV or infrared? I believe some animals can see a little bit in infrared. They can definitely have a better night vision than we do. Some of them do. So I think they can see a bit in infrared, but I'm not an expert on this. We would need to check more. In ultraviolet, that's a good question. Very good question. I would know. I would need to ask biologist. Maybe if some of you know, please write it down because that's interesting. And as we do that, let's move on here. Andromeda Galaxy. Sometimes when we write optical, that means visible light. So it just means that this is a regular image. When I say regular, I mean like, the kind of we're used to, visible light image. But here we have the infrared image of the Andromeda Galaxy. And here we have the X-ray image of the Andromeda Galaxy. And sorry, I just see that Gavin wrote something. Bees can see in UV and even humans if it absorbs by the lens. Huh. I didn't know that. Thank you. Thank you, Gavin, for providing an answer. Okay, so coming back to the Andromeda Galaxy, what's interesting here is that in infrared, we can see most of the gas. What's glowing here is mostly in the spiral arms, and those are regions with a lot of gas where new stars are formed. So we're kind of seeing the stellar nurseries where new stars are formed in the infrared. Now, if we look at the X-rays, most of the points that you see there actually represent the opposite, sort of dead stars that have turned into pulsars, neutron stars, and black holes. So black holes, can be the final stages of very massive stars. And if they happen to be in binary systems, so two stars are orbiting one another, one ends up being a black hole, so the other one has matter sort of falling into the black hole. It heats up a lot, provides a lot of energy, and it ends up emitting X-rays. So some of these sources that you see here, X-ray sources that you see here, are black holes, matter falling into black holes. So we're seeing very old dead stars here, and we're seeing new stars. And in the optical light, then we're mostly seeing sort of regular life stars, like our sun, for example. It glows in visible light. So we can see different stages of the life cycle of stars and different wavelengths. And here we have the composite and infrared and X-rays, and all three of them right here. Thank you, everyone, for providing answers about birds and animals seeing UV or infrared. Here's another example, the Whirlpool Galaxy M51, a beautiful galaxy. Here's a visible light image. Again, here's the X-ray image. And again, some of these sources would be black holes in binary systems, very hot gas glowing in X-rays. So there are different processes happening here. And sometimes this is called like high energy astrophysics, because we know for something to emit X-rays, it has to have a lot of energy. X-rays are very energetic rays. So it's what's happening there is sort of not regular stars glowing, for example, invisible. It's not like the sun, so you would have something much more energetic to emit X-rays. So basically what that means is that we now have telescopes detecting light across the spectrum. When we think about telescopes and observatories, usually we think of the white domes that we have on different places on Earth, and those can see visible light. But these are just a tiny part of all the telescopes that we're using now, all the observatories that we're using. So this image is from NASA. It's actually mostly showing NASA's telescopes across the spectrum, but you can see some of them in visible light, including Gemini, which is in part Canadian. You can see here the Hubble Space Telescope, which sees mostly in visible light as well. But you can see some infrared telescopes and microwave telescopes and radio telescopes. Radio telescopes, here we have some on the ground. And if we go on the other end of the spectrum, then we have Chandra, which is an X-ray telescope, and we even have gamma ray telescopes. So now scientists have found ways to study the universe across the spectrum, and it opened up many different windows in terms of what we can observe and what we can detect. As you might see here, some of them appear to be satellites, in orbit. Some of them appear to be on Earth, And there's a reason for that, is that some parts of the spectrum don't make it to the ground. Luckily, we're happy with that, because that would be, I don't think we would be here if gamma rays and X-rays would make it all the way to the ground. They're blocked by the atmosphere. And that's what this slide shows you. It's the opacity of the atmosphere. So again, across the spectrum, so we don't see colors, we don't see, you know, the different parts are not written, but you can tell visible is here. Visible mostly makes it to the ground. This is the opacity, so that would be 100% opaque. It's not down to 0 exactly for visible light because there's some atmospheric distortion. So yes, we can see the sky, but there's always some distortion due to the atmosphere. Radio waves make it to the ground without any problem, but very long radio waves are blocked, and then most of the infrared is also blocked by the atmosphere. Some telescopes in cold places and high above the ground can detect some infrared, but it's a bit tricky and depends where in the infrared as well. And then gamma rays, X-rays, and ultraviolet mostly are blocked on the surface, so you have to have satellites. You need to observe them from space. So some ultraviolet, of course, makes it to the ground because that's how we can get sunburn, but a big fraction of it is blocked in the atmosphere. So that's why we have some telescopes in space, and so we can detect those kinds of wavelengths that don't make it to the ground. But that's a very good thing. We don't want, again, gamma rays and X-rays hitting the ground. Okay, now let's talk about spectroscopy, which really is the art of decoding light. What kind of information can be hidden in the light? And I see time is going by very quickly. So spectroscopy is basically just the art of creating rainbows. Here's white light coming into a prism, and you get a rainbow, what we call a spectrum in science. So there are different types of spectra, spectrum. So a continuous spectrum is when you have all the colors. So when you look at a rainbow, this is what you imagine. Usually all the colors are there. And that's sort of created by a hot object or different sources. I don't want to go into all those details, into too much details on this, but what I want mostly to show you is that if you have a hot gas that's glowing, for example, those fluorescent lights, neon lights that we call, you put a gas in there, you throw electric current, it makes the gas glow. Then if you look at the spectrum, it will look something like this. It will have very discrete lines or bands, and this is what we call an emission spectrum. And I'll come back to that in a minute. But usually what you use in astronomy is sort of a mix of both. So if we have, we'll look at an object, for example, that has a continuum spectrum that will emit light at different wavelengths, but something will absorb the energy at specific wavelengths. So you'll have some dark bands in there, and this is what we call an absorption spectrum. This is the one that's most used in astronomy and actually in many fields as well. So I don't want to go in all the details, but I found when I did this presentation before, I found that some people were confused in some of the next slides. So I wanted to show you that sometimes, for example, if you detect hydrogen in an object, it will have very specific lines at certain wavelengths. But if you had a hydrogen by itself glowing, then it would have lines at exactly the same wavelengths, except that it would be glowing instead of being absorbed and showing up as a dark line. So I just want you to see that the wavelengths are the same. It's just depending on what happens with the gas exactly. Is it glowing or is it absorbing some of the light? So how do we know about the composition of those objects? Well, I kind of told you already. For example, if you look at a rainbow, you know, a rainbow outside is basically a spectrum of the sun. It's light from the sun that's split into all the different colors. Well, usually when you see it in the sky, you don't see it in super details. But if you could have it projected on a wall, for example, and on a white wall with a lot of details and very good contrast, you might be able to see dark lines in the spectrum. And these lines are represent some of the elements found in the atmosphere of the sun. So the two lines here represent sodium, and the hydrogen line right here, that's hydrogen alpha, the main hydrogen line. So this is how we can find out what objects are made of, is by looking at the spectrum. And what's interesting is that each element or molecule has its own spectrum. It's like a fingerprint, allowing the identification of objects. So here you can see hydrogen, for example, the specific lines of hydrogen and sodium. We have the two yellow lines here, and helium. I've worked in a lab where we used molecules a lot, and they had a lot in the infrared, absorption lines in the infrared. So basically, every element or molecule has its own spectrum, and scientists simply need to compare the lines that they observe in an object with those catalogs of spectral lines, and they are able to find out what's in those objects. So let's have a look at some examples. But first of all, how do scientists do this exactly? Well, I like to say that scientists turn rainbows into graphs. It doesn't sound super romantic this way, but this is exactly what we do. Instead of looking at the spectrum directly, astronomers use a graph showing the intensity of light as a function of wavelength or color. So here you have, this is two ways of representing exactly the same thing. We can put it in colors with, the different wavelengths showing as colors. But you could turn it into a graph. So basically for every line here, we're looking at the intensity, vertical line in a sense. We're looking at the intensity. So is there a lot of light? And maybe here it doesn't show to the eye, it gets fainter. But here we can definitely see some dark lines, which appear as lower intensity. And this is simply the wavelength increasing from green to red. So this is how scientists look at a spectra. It's not as pretty as looking at beautiful images of the sky. I remember when I worked at the observatory in Victoria, and when the telescope was set up in spectroscopic mode, definitely for the public that was not as interesting. But this is how a lot of science is done because you can get so much information from a spectrum. So here are some examples. This is real data from the Canada-France-Hawaii telescope. Here we have the wavelength. It's given in Armstrong. It's just another unit. It's sort of the nanometers, 10 times smaller than nanometers. So this would be 655 nanometers. And we have so the spectrum, the intensity here. This is the main spectrum is around 1, and definitely see a big spectral line here and another big one here. And actually, because of those catalogs that we have, scientists might not be able to, well, especially people who start, like if you've been looking at those wavelengths for a long time, you'll know eventually that this is hydrogen. But when you start, you don't know, so you need to look at a catalog of spectral lines. But this one is hydrogen, and the other one here is helium. When I did, actually, if I remember right, this is actually data that I've used when I did some of the research. We studied a lot this helium line right here. Another example here is Io, the moon of Jupiter. So they're just comparing here 3 different spectra. So this is the lab spectrum for sulfur dioxide, SO2, ice, and these are 2 measurements of IO. And basically just this one here, you can see that it has a very specific absorption line, and we can see this line in the 2 spectrum and the 2 spectra of IO. So we can tell that there's some sulfur dioxide ice on the surface of IO. So this is how we can tell what elements are made of, is simply by looking at the spectra and finding where those spectral lines are. But again, when we look at spectra, it looks more like this and not the beautiful colored version like this. That's how science is done. There we go. Okay, now how can we tell the temperature of objects as well? Again, the spectra can help us, but also the color. And as you'll see, the color, it ends up being mostly a lot of the color of the objects. Something that it's interesting to understand is that the hotter the object, the more light it emits. If it, for a star, the same size, same surface area, in a sense, if it's hotter, it will emit a lot more light than if it's cooler. And this is a bit what we see here. This is kind of the intensity of the light emitted by different objects. You can see an object that's at about 3,500 degrees Kelvin. That's, around, it's close to Celsius. That's around 3,200 degrees Celsius. So it emits some light, but not as much as an object around 5,000 degrees, which would be a 5,500. And here, it would emit a lot more light. And also, the peak wavelength shifts toward higher energy. So right now, the peak wavelength, where you get the maximum intensity, is in the red. Here, it's more in the orange, and orange again in yellow and green. And an object much hotter would be closer to the blue. So the hotter the object, the bluer it is, towards the blue end of the spectrum. So I'm trying to explain this graph simply this way, but what that means, how that translates, is that simply by looking at the colors of the stars, it gives us clues about their temperatures. Blue is hotter than red. For example, we have a very hot star here, a blue star, which would be around 30,000 degrees. And here we have a what we call a cool star. Again, it's not really cool. It's still very hot, 3,500 degrees, but much cooler than the other one. I should probably say less hot than the other one. So simply by looking at the colors of the stars, we can tell if they're hot or not. And it all comes down to a bit this graph here that the hotter the object, the peak wavelength shifts toward the blue part. This is actually the temperature of the sun. And you can see the sun kind of peaks in the green. Why isn't the sun a green star? Simply because if you have green is kind of the middle of the visible part of the spectrum, so we see it mostly as white. And the sun would actually be a white star. It appears kind of yellowish because of the effect of the atmosphere. But if we're outside in space, it would mostly look white. I see a question here. Outside of visible and infrared, do other electromagnetic regions show emission and absorption line? Yes. I've never seen really an X-ray spectrum, so I can't tell for sure. But yes, there are some in ultraviolet. And again, I've never... No. There's some in radio as well. I know there's some, I just kind of hesitating here because I don't remember seeing the same kind of graphs with different types of radiation, those different types of radiation. But I know, for example, one very important line that we use in the radio is a hydrogen line at a wavelength of 21 centimeters. So 21 centimeters, those waves, and it's from hydrogen, and it's used a lot in radio. So I won't say more because I'm not sure exactly how it's all done and all detected and so on, but yes, we see them in different fields. Okay. Okay, I'll go through that quickly. I just wanted to show that when people started cataloging the spectra of the stars, and actually many women were hired to do that about a century ago, to classify the spectra of stars, and they found that many of them, there were different types, there were different categories. Many of them would be similar to this, for example. Other ones would have more spectral lines, and some other would have many, many more spectral lines. These are just name of stars that are representative of these categories, but they have like O-type stars and B-type and A and F and G and so on. And eventually they realized this depended on the temperature of the stars, and they realized that the O stars were the hottest and M stars were the coolest. But classifying spectra at first in those categories revealed a lot about the stars themselves, about how they evolve even at some point, and how they emit light and so on. And we find out that the O stars are very hot, very luminous. They emit a lot of energy. So here we have a blue giant. Those would be sort of a star during the main part of its life. So they're not near the end of their lives. So O stars would be very hot, very massive, emit a lot of light. And then you would have the M-type stars, which are red dwarfs, a lot cooler, a lot less energy. But these are a lot more frequent than O-type stars. And the sun would be a G2 type star. So we found that there are many different types of stars this way by looking at spectra, and that helps us. There's a whole lot that depends on those, on that classification and understanding of stars by looking at the spectra. Okay, one final thing I wanted to tell you how we can figure out. I know I'll go over the hour. I apologize. I guess I had too many things to say. I always try to cut, and there's always too many interesting things to tell you. The speed of objects. So how do we know about how objects move? Of course, objects on Earth, we can see them move. I know they're at one place, and then a bit later they're at another position. We don't really see that with objects in space very far away because they're so far away that we don't see that difference in position. But we can figure out how fast they're moving from what we call the Doppler effect. The Doppler effect, so here you have a light source, or it could be any wave source, anything that emits a wave as it's moving. So you can imagine, you've seen that before. If you throw a rock in water, it emits waves and you can see the concentric circles around it. So imagine that, but now if you have the moving rock, And well, you've probably seen that, let's say, from ducks moving around. So the circles are not concentric anymore, and as the source of waves moves, and I'll show you the animation, the waves in front of the source are compressed, while the waves behind the source are stretched. And you can see that here. This is what we call the Doppler effect. The Doppler effect has applications, actually affects all kinds of waves. It affects sound waves, and you're familiar with that all the time. If you're on the side of the road and there's a car passing by, it will do something like, I'm not really good at doing the sound here, but you know, the pitch changes as it passes in front of you. So it has a higher pitch as it's coming towards you, and then a lower pitch as it's moving away. So higher pitch means shorter waves, higher frequency, and then as it moves away, then it has a lower pitch, longer wavelengths. So same thing happens with light. So if we talk about light here, so waves, no, sound waves is a different thing. I just wanted to say that this effect, the Doppler effect, can be seen in both light and sound. But let's forget about sound for now. Now, if we look at light, if the object is moving towards us, the light is shifted towards shorter wavelengths, and what we call sort of higher pitch with the sound, with the light would be a bluer. It would be a blue shifted. If the object is moving away from us, then the light is shifted towards longer wavelength, and this is what we call red shifted. Again, its equivalent for sound would be a lower pitch. So what happens for real when we observe the sky is that if you're looking at a spectrum, let's say we have a spectrum of a cluster of galaxies that happen to be very far away, but you see those spectral lines, and they're not exactly at the same place as some of those lines that you would see in the sun, for example, or an object that's not moving in a sense, like not very high speed compared to us. You can see here those two lines here that are between blue and green. Here are definitely in the green zone. This one here is shifted within the red part of the spectrum. So what that means is that we can tell that this object, because they're red shifted, the object is moving away from us. So if those lines are all shifted towards the blue, we could say the object is moving towards us. If they're all shifted towards the red part of the spectrum, and then we know it's moving away from us. And this fact, this observation, is what is how scientists came up with the idea of the Big Bang, because we could see that all galaxies were moving away from us. All galaxies, except the ones that are closer to us, like very far away galaxies, are moving away from us because all their lines are red shifted. The spectral lines are all red shifted. And we can measure the shift pretty precisely, and there's a simple equation actually starting from how much it's shifted that translates back into a speed or velocity for those galaxies. We can do that. I've done those calculations during my studies. So again, how do we know objects are moving? It's because it's either red shifted and blue shifted, but I just wanted to highlight that's some of the basic information that we got that led to the idea of the universe expanding, everything moving away from one another, which as the basis for the idea of the Big Bang. So there's a lot of information encoded in light, as you've seen so far. The type of object, we can already say a lot about the type of object just looking at the spectrum type. There will be some emission lines sometimes in objects, so that tells us a lot already about the object. Mostly it's absorption lines, though. We can look at images at multiple wavelengths, and that will give us clues about what's happening as well, how energetic it is, and so on. Its temperature, again, either the spectrum or the dominant color, just like I told you for stars, the blue star or red star. The composition, definitely spectral lines. This is so useful in many different fields, but especially in astronomy since we can't take samples. We can tell the speed or its velocity thanks to the Doppler effect on spectral lines. And there's a lot more. I mean, we can tell if stars are rotating. I didn't go in all the details. We can even decode in the light if there's exoplanets around the star. And I didn't talk about that at all, but hopefully you'll sign up for our next webinar, and Jason Rowe will tell us more on May 17th about how we find exoplanets, even though we can't see them directly. Oh, Ed, you have a very good question. So did Hubble not say that the further away a galaxy is from us, the faster it is moving away? If yes, then is that not faster than light speed? Actually, it appears to be more. It can actually, some galaxies can appear to be moving away from each other faster than light speed because it does not violate Einstein's principle. It's because galaxies moving, and I won't go into all the details of the Big Bang, but galaxies moving away from one another, it's not, it's actually not technically the galaxy itself moving, it's the universe expanding. It's empty space getting bigger. And okay, I won't go into more details, but basically that explains why they can appear. It's measured similarly with the Doppler effect, but it's actually not exactly. Maybe I shouldn't have gone into that topic. It's more complicated. Let's leave it there. Okay, I know I'm over the hour, but I had a few more slides, so if you have to go, you can go. What I wanted to show you is how we get those nice astronomy pictures that we see sometimes in magazines or on the web and everywhere. So if you have a few minutes to hang around, I think you'll like this. The main thing is actually that telescopes actually see in black and white. Well, it's not the telescope itself, it's the camera. The CCD cameras that we put on telescopes give us an image in black and white. Why don't we put color cameras? It's because we get more information. They're more sensitive if we leave them in black and white. And it's the same kind of technology now that we have in cell phones and tablets and so on. Those are small CCD detectors. And that was actually driven by astronomy. The technology that we now have in our homes was driven by astronomy because we needed to have very sensitive detectors. But anyway, in your phone, we put it in colors right away, but scientists, most of the research can be done in black and white. So how do we end up with a nice color image if this is the raw image from the Hubble Space Telescope, in this case for Hubble? Well, here's how it's done. And there's a website from Hubble that shows us this process from many different images. So I'll give you the link afterwards. So what they did, here we can see, for example, ultraviolet light, visible light, infrared. So Mars will have light from all those wavelengths. But what we do is that we put a filter. So we put a filter before the camera. Let's say we put a blue filter. It means only the blue light will go through the camera and we'll get an image like this. This shows us the blue light from Mars. We do the same thing in green. We only get the green light from Mars, and then we do it in red, and here's the red light from Mars. You can already tell that Mars is probably more red than blue because it appears brighter here. So there's more light that hit the camera in this image than here. Then we apply colors through a program like Photoshop or other ones, and then you can probably imagine what we do. We combine them all, and we get this. When we combine colors with light, it does make it brighter. So for example, those three spots here that have almost equally blue, green, or red, like the polar caps, will end up being white. If you try it I remember as a kid, I was told if you combine all colors, you get white. And I thought, that doesn't work. I'm trying with my crayons and I would end up with brown at the end. It doesn't work with crayons, but it works with light. So if you combine equal amounts of red, blue, and green, you get white light. So here you get a visible light image, which represents natural colors, what our eyes would see. Sometimes, though, we take pictures to give us different details, and we end up creating a color image. But it's not right. It's not quite natural colors. So in this case, this is another famous image by the Hubble Space Telescope. We took a filter in green and two of them in red. And here, what we wanted was not so much to have a nice, real color image, was mostly to see the light emitted by specific elements. So we pick the wavelength from specific elements, so some emission lines from those elements. We had a very narrow band filter that just was looking at that light specific that would show us where that element is in the nebula. And then we decided to assign a color to it. So this one is not really blue, and this one is not really green. This one is sort of in the red, but we apply different colors to it and we combine them. So this represents a visible light image, but it's false colors. And I like to mention that the goal to have false colors is not to deceive people or create something fake. It's just that scientists wanted to look at where the hydrogen and the oxygen was and the sulfur. And because they had three images of this nebula, they decided to combine them and apply colors and create something. We could have color coded it differently. And it would have been beautiful as well. It wouldn't be right colors, but it's interesting in this case to see the final image. So here, the blue and green were represented the hydrogen and sulfur, and the red was where the hydrogen and oxygen, and then the red was where sulfur is. Sometimes we even do something differently. So here, this image, the three images here were taken in the infrared. So three different filters, but this is the kind of light we wouldn't see with the naked eye or with our eyes. It's not visible light. But we know here there's more, these two look quite different. So there's probably some elements that glow on this part here at this specific wavelength that we can't see here. So anyway, we get three different images, we apply colors to it, and then we combine. So this is an infrared image in false colors. Again, we kind of color-coded something that we couldn't see with our eyes. But in this case, there's a lot of scientific information. Green and blue, which ends up being this part mostly, shows us light reflected of the dust surrounding the stars, and in red, it's the hydrogen gas cloud around this star. So it gives us different scientific information. So this is how we get color images by taking three pictures and combining them. And if you want to play with that site, I like it. Actually, it's on the Hubble site. It's a bit old. It's not on its most recent pages, but you can play with it and kind of remove one color and add it and see what happens. The Chandra telescope, an X-ray telescope, also has multi-wavelength images. If you click on this link and then if you click on some pictures, you'll have tabs where you can say, just show me radio, just show me X-ray, just show me visible. And it's very interesting to see the differences. Some of the pictures I showed you came from there. Our module I showed you, which uses UV, ultraviolet, and visible images of the sun in Helio Viewer. So you can check it out. That's on our website. And also have this link from the European magazine Science in School. At some point, they had many activities on light, not just about astronomy, but just light in general, if you are interested. And that covers what I want to show you. So I knew I would be over the hour a little bit, but I thought I should cover those last few slides because that's often a question that people get. How do we get those color pictures, especially when they learn that the raw data is in black and white? I thought it would be interesting. I know I found it very interesting when I created my first color images using the Plaskett telescope in Victoria. I got nights on the 1.8 meter telescope, and one of my goals was to create nice color pictures like this, but I learned a lot through the whole process of how it's done. So now I know which looks more like real colors or false colors when I see pictures, and I understand that false colors are not just to deceive people. Okay, questions. If you have to go, thanks a lot for coming and watching us, and if you watch the recording, thanks for watching till the end. If you have some questions, if you're live, just type them down right now. I will go over them. And if you're watching the recording, you can just email me if you have any questions. So Ed, if we could travel to these objects, would our eyes see them in color as we got closer? This is a very good question. Mars, obviously, we can see in colors. Hold on, if I come back to Mars. So Mars we could see in colors. I mean, we see it already in colors. But for example, this nebula, it is, if you were within that nebula, you probably wouldn't see much gas because it's such a thin cloud. So we need sort of light years thick of that cloud to see the color. It's a bit like if you're in, if you're in a fog, you can see things around you quite well. But then if you look far away because you're looking through more of the thickness of the fog, then you can see that it's thicker. I think if we were very close to this nebula, we wouldn't see the colors super well. I don't know exactly. Sometimes I try to imagine like what distance would you need to be able to see it. So you're close enough to see it well, but not too close so that there's not part of it. I don't really know the answer. But yes, these objects would have, for example, the Orion Nebula, it's one of those nebulae you can see with the eyes. If you look through a telescope directly, you see some colors on it. It's not super obvious, but if we had a nebula that was closer to us, then we could see it as a patch of colors in the sky, for example. So yes, the colors are real, not exactly like the one we see there. This one is false colors. But it is a good question. I've seen people debate about that a little bit, and there's no real answer on how they would appear exactly if you were close. Gavin, your question, is there a maximum light frequency? That's a very good question. I don't know the answer. I don't know the answer. I, in a sense, it seems like it can go. Hold on, where is my electromagnetic spectrum? As we go higher and higher here, you get shorter and shorter wavelengths. In a sense, like if you get to the limit, like the Planck length for the wavelength, that might be, in a sense, the limit in terms of short wavelengths. That might be the limit in terms of frequency because it's inversely proportional. That's a very good question. I'm not sure. Hmm. Never heard of anything around that, actually. I'll have to check. I don't know. Just on top of my head like that, I don't know. I see. Oh, I forgot my water bottle. I was gonna have a sip of water as I wait for some of your final questions. Maybe Google. Here, I'll try Google while I'm waiting for the next question. Um, okay, so I don't see any more question. Oh, here. Does light have a frequency limit? Well, you know what? I won't. This seems to be from a physics forum, so I haven't had time to read it. But there, if you want to check this out, there might be something here. I'm kind of curious. But anyway, I don't have time to read it all, so just check it out, and maybe Google can find the answer. I don't know it. Thanks a lot, everyone, for coming. Join us for our next webinar in May with Jason Rowe. That should be very interesting. I love exoplanets. I find that it's a very fascinating field of study. So if you are interested, make sure to register. And if you are a teacher,